So not only is standard deviation the square root of the variance, it's also a measure that measures how much data varies about the mean. Okay, so it tells you how much the overall set of data varies about the mean of the set of data. So what are some properties of standard deviation? Well, standard deviation is always non-negative. Does non-negative mean positive? Well, I guess it in your brain you probably think so, but it just means the reason why they state that way in the book, if something is non-negative, then it's 0 or a positive number. So it can be 0. If all of the data items are the same in the set, then the standard deviation is going to be 0 because the items don't vary about the mean if they're all the same. You know, if everybody in here made a 100 and I found the standard deviation for that set of data, it will be 0 because you're all at the mean of the set of data. Okay. The standard deviation can increase big time or dramatically, that's not a word, dramatically if you have an outlier. So, you know, again, if let's say I took 10 people in here and 9 of you had an A on the test and 1 of you made a 20, that would affect the standard deviation big time because what happens? That outlier affects the mean, and then we use the mean to calculate the standard deviation, right, in the formula. So it really affects the standard deviation. Outlier does. And of course, standard deviation is going to be in the same units as whatever the data that we're working with. If we're working with a set of data and it's heartbeats, maybe heartbeats per minute, and my standard deviation was 3.4, then that would be 3.4 would be in the same heartbeats. It'd be that many heartbeats would be the standard deviation, or the that's how the heartbeats would vary about the mean of the set of data. I would have to say, and your book agrees with me, and I'm glad it does, that variance and standard deviation are the most frequently used statistics. Okay. Now, why is that? Well, if we have a set of data that the distribution is bell-shaped, do you remember, like when we looked at the histograms and those types of representations, how I think I mentioned bell-shaped would be like if it kind of if you could draw some shape like that over it. If we do have a bell-shaped distribution, then, and this is called the empirical rule. If we have a bell-shaped distribution, then about 68% of the data items will lie within one standard deviation of the mean. So in a set of data, the mean would be right here in the middle if it was normalized, or if it was bell-shaped, the mean is in the middle. And so if the mean is right here for our set of data, it could be x bar or it could be mu. And the area under this curve, the total area under this curve is 1 or 100% of the data items, then within one standard deviation of the mean, so that's one standard deviation above and one standard deviation below, you would have 68% of all of the data items. Okay, so all of this here within one standard deviation, that's 68%. Again, that's one standard deviation. the empirical rule says that you will have 95% within 2 standard deviations. So if you have your bell-shaped curve and the mean is right here in the middle, and you go 2 standard deviations, so if the mean is right here and we go over to the right 2 standard deviations, and we go over to the left 2 standard deviations, then all of this data, or the amount of data in between, would be 95%. And lastly, 3 standard deviations, and all this should be on your PowerPoint, I would think. Look at your PowerPoint for this section. Yeah, the pictures aren't, but it's at the top of the 4th page of this PowerPoint. So if we have, let's see, a bell-shaped curve, we have the mean here in the middle, and we go out, let's say 1, 2, 3 standard deviations each way. See, that's the mean. 1, 2, 3 standard deviations. So that would contain 99.7% of all the data items. Again, that's 3 standard deviations. All right, let's look at this word problem. You don't have to write this down. This is in your ebook. I think it might also, yeah, it's also on your PowerPoint. All right, so good. All right, it says, suppose a group of high technology stocks has an average earning per share of $6.26 with a standard deviation of $1.37. If the data possesses a bell-shaped distribution, which interval contains 98% of the earnings? So we want to actually write the interval down that would contain, I said 98, 68% of the earnings. All right. All right, so here's the mean we have. We have X bar. The mean is $6.26. And we have the standard deviation is $1.37. So if we want to write an interval that has 68% of all the earnings, then what we need to do, we know that 68% corresponds to 1 standard deviation. So we need to add and subtract 1 standard deviation from the mean. So we want to say X bar plus S, which would be 6.26 plus $1.37. All right, and that would be what? All right, is that right? $6 or $7.63. So that would be the top part of our interval, because that's the bigger number. And then we want to take the mean and subtract the standard deviation. And we're only doing it 1 standard deviation because it wants to know the interval for 68% of all earnings. All right, and so that's going to be $4.89. So the interval, I don't know exactly how you would want to write that. Usually with intervals, we can write them in parentheses. This isn't an X and a Y value. This is just an interval. So it will be from $4.89 to $7.63. That would contain 68% of all of the earnings. All right, which interval contains 95% of all the earnings? So if it's 95%, then all of the earnings would be within 2 standard deviations of the mean, right? So we need to say x bar minus 2 times the standard deviation and x bar plus 2 times the standard deviation. That would give us the interval that we would have 95% of all the earnings, because 95% corresponds to 2 standard deviations about the mean. So that would be 626 minus 2 times 137, and 626 plus 2 times 137. Do that in the calculator. And it looks like the bottom number is going to be $3.52, and the top number is going to be $9 exactly. So the interval would be from $3.52 to $9. All right. So that's the empirical rule. But the empirical rule only applies to bell-shaped distributions. So if your distribution isn't bell-shaped, then what do we do? How can we calculate how much of the data is going to be, a standard deviation within the mean, or what percentages would it be? Well, there was a Russian mathematician that figured out another way. All right, and of course these are approximations, but his name was Chebyshev, or her name is his or her. I don't know. I don't have a picture here, so I'm not sure. This is Chebyshev's theorem. All right, so Chebyshev's theorem, your standard deviations have to be greater than 1. So we only have percentages for 75% and 88.9%. Okay, so 75% of the data lie within 2 standard deviations of the mean. 75% lie within 2 standard deviations of the mean. And 88.9% lie within 3 standard deviations of the mean. Now this is on your on the PowerPoint. Look at the formula you have to use. It's in the bottom left-hand corner, page 4. So it says it's 1 minus 1 over k squared for k greater than 1. So we can't use 1. It has to be greater than 1. Now that we could use like 1.1, right? We could use a decimal, because decimals exist, right? So it doesn't say we have to use whole numbers. So we could use a decimal, but I think for the most part, what you have to do with this is you'll either have to associate 2 standard deviations with 75% or 3 standard deviations with 88.9%. All right, let's look at this example with Chebyshev's theorem. This is on your PowerPoint, page 5 of this section. And I say page 5. If you pull this off the website, it depends on how many of these figures you print off per page. So I think I usually print 4 or 6 to save paper. Default is 1 slide per page. I just didn't really see that as being worth it. All right, and so your PowerPoint does actually have a picture here. Let me see if I can find the picture. I like pictures. All right. All right. This is the age distribution histogram for New Jersey in 2017. I mean, it's not, I wouldn't say that this was bell-shaped, but it could almost be bell-shaped, but it's not quite. And it says the mean of the data is 37.2, while the standard deviation is 22. What can we conclude from Chebyshev's theorem using k equals 2? All right, so k equals 2, that's 2 standard deviations. What is the percentage that we know goes with k equals 2 for Chebyshev's? It's 75%, right? So 75% of the people will be within 2 standard deviations of the mean. Their age will be. So if we want to know, and I believe if you look where when they work this out, we're talking about the entire state of New Jersey. So that is their population. They're not really thinking of it as a sample. So instead of x bar, they're using mu. So if we want to know like an interval, it'd be mu plus 2 times the standard deviation, because k equals 2, and mu minus 2 times the standard deviation. All right, so the mean is 37.2, so it'd be 37.2 plus 2 times 22, and 37.2 minus 2 times 22. All right, so 44 plus 37.2, that's 81.2. Wait, I put that in the wrong place. Equals 81.2. And then when you subtract 44, well, we're talking about ages here, but if you use your calculator, you get negative 6.8. You can't have an age of negative 6.8. So what would that mean? That would mean that we'd have to really think, if we were talking about ages, it'd be 0, right? So that'd be newborn. So 75% of all ages in New Jersey are between 0 and 81.2 years old. 75% of the people. So there must be 25% must be 81.2 or older. It's hard to believe. All right. I don't know if I believe it. Of course, it's an estimate as well. So, estimation. Now, if we look at different sets of data, like say that we had this information on New Jersey, this set of data, and then we had the same information on Mississippi and the same information on Washington and the same information on South Dakota. Well, how could we compare those sets of data? Because you're going to have different amounts of numbers, different amounts of data items, maybe different factors. Well, one way that people compare sets of data is by using something called the coefficient of variation. All right, and the coefficient of variation is, and the abbreviation is CV, it is the standard deviation divided by the mean times 100, and then you write that as a percent. So that's if we have a population standard deviation, a population mean, and this is if we have a sample standard deviation and a sample mean. It means the same thing. One thing that happens there when you take the standard deviation and divide by the mean is that you lose the unit goes away. So because remember, these are all in the same unit. So since the unit goes away, then this can be used to I guess compare apples to oranges because the unit's going away. We don't have to compare just apples to apples. We can compare apples to oranges then. You can imagine it does take a little while to do this because what do you have to do? You have to calculate. If you're not given the standard deviation, you have to calculate the standard deviation. And then if you're not given the mean, you have to calculate the mean. Of course, you're going to have to calculate the mean to find the standard deviation anyway. All right? But you simply divide, say it times 100, and get a percentage. Okay? Let's read this. I know you don't have anything else in your PowerPoint, but let's read this, what it says about coefficient of variation. It says, one of the primary focuses of quality control in manufacturing is the reduction in variation of the output process. Have you ever put together like a swing set, or if you're like me, a dollhouse or something like that, and then you get to putting it together and all of a sudden one of your bolts just won't fit, or maybe it'll fit but it is too small, and so it when you put it in, everything just wiggles around. Well, it's important to companies that whenever they cut these bolts and they cut these screws and everything, that they are very precise to whatever measurement they need. Or if they're cutting holes in a board, I was putting together that dollhouse and I was getting so mad. But if they cut holes in a board, it's important that all of the holes have to be the right diameter, right? So that's this problem's talking about. It says one of the primary focuses of quality control in manufacturing is a reduction in variation of the output process. A bolt manufacturer wants to compare the variability of two bolt manufacturing processes. One process creates bolts with a mean length of 2.5 centimeters and a standard deviation of 0.2 centimeters. So it's already calculated for us. Is this process more variable than one that produces a bolt that has a mean length of 1 inch and a standard deviation of 0.052 inches? So you can see the measurements are completely different. The standard deviations are completely different. But we can look, say we have two different machines and we want to know which one is cutting the bolts correctly or has less variability. Then we take the information from bolt 1, we take the standard deviation, divide it by the mean, and say it times 100, and you get that the first machine has an 8% variability. The second machine, you take the standard deviation, you divide it by that 1 inch, you say it times 100, you can see its variability is 5.2%. So the coefficient of variation for bolt 1 is 8%. This means the variation is 8% of the mean value. The coefficient of variation for bolt 2 is 5.2% of the mean. Therefore, the process used to make bolt 2 is less variable than that for bolt 1. So I guess they're not talking about two machines, it's different processes to cut these bolts. But you want less variability if you have a product, right? Especially one that is going to be mass produced. You don't want there to be a lot of difference